Okay, we're continuing on here, chapter 17, I believe. And we got into a little bit about redox reactions. Again, as I mentioned last time, we're going to kind of go over some of the basics of redox reactions, including how to balance them. Again, just to make sure everybody's on sort of the same page. And then we'll get really into the heart of the chapter, which is about galvanic cells and electrolysis. So redox reactions are oxidation reduction reactions. And as we talked about, oxidation basically means losing electrons, and reduction means gaining electrons. And as we talked about last time, there are a couple other definitions for each of these. We don't usually come across it too much here in general chemistry, but again, if you go take organic next, maybe um, we do have some other definition of oxidation, which involves oxygen and hydrogen, and also reduction, which involves gaining or losing oxygen and hydrogen. But here we kind of focus on mainly the electrons. And again, when you look at the oxidation state of a substance on the left-hand side of the arrow versus the right-hand side of the arrow, if you follow its oxidation state, you could use a basic number line to figure out what is being oxidized, what is being reduced if you're not sure. When you do lose electrons and become oxidized, you then become more positive. So if you look at the oxidation state of that substance and it's moving in a very bad drawn arrow in that direction towards the positive side there, then that thing is going through oxidation. If you look at the oxidation state from the left-hand side of the arrow to the right-hand side of the arrow and it's kind of moving towards the negative side, that's going to be reduction. And the good thing is usually these happen always together. So if somebody's being oxidized, somebody else is being reduced. So really you only have to figure out basically one of those things, what's being oxidized and what is being reduced. In addition, we talked about oxidizing agents and reducing agents. And again, remember that these are basically different than their names or opposite of their names. So the oxidizing agent is the sort of substance that gets reduced, while the reducing agent is the substance that gets oxidized. And again, essentially, the reason they're called that is when they get reduced, it has to cause somebody else to lose electrons. So they're causing the oxidation in that other species, and vice versa. If they get oxidized, that means that they will release their electrons and somebody else will pick them up, and that's going to cause the reduction in the other thing. So, as we talked about last time, those are different questions. If you're asked that, there are different questions of what is being oxidized and what is being reduced. And that's a different question than what is the oxidizing agent and the reducing agent. And again, sometimes people kind of get those things confused. Um, and then I think I sent you home at that point, right? Any questions on that? All right, let's continue on with where I think we left off, which is how do we officially sort of identify the oxidation number? Are the oxidation state is sometimes referred to. And there are several rules that we typically follow. The oxidation number or state is really the charge the atom would have in a molecule when if the electrons were completely transferred. Now, oxidation numbers and oxidation states are sometimes different than what we sort of have in our head of the charges associated with certain elements. And what I mean by that is in an ionic compound, for example, we think of chlorine as always being -1. And it definitely is in an ionic compound where electrons are going to be transferred from the metal to the non-metal. But when chlorine, for example, hooks up in a covalent situation where they're sharing electrons with other elements, they actually can take on an oxidation state that's more positive. And it can be something like +2, 3, 4, and so forth. So sometimes people get a little bit confused on that because, we beat into your head the ionic ions and the charges. But when we're talking about oxidation state, it does make a big difference in terms of if it's an ionic compound or if it's something that's covalently bonding or sharing electrons. And, you can get some things that we normally associate as being positive and have negative oxidation states and vice versa. And things that are normally negative can have sort of positive oxidation states. Now, the first rule pretty much is straightforward. It's pretty much anything that's sort of in its natural state, uncombined, not attached to anything else, will have an oxidation state of 0. So if you have any metal or anything like that just by itself, it's not going to have a charge. That also is something that people have trouble with sometimes. A reminder that if you have anybody from the periodic table by itself and not attached to anything else, it has no charge. So it has a 0 oxidation state. Again, things only really get charges, for example, when metals and nonmetals come together. If we do have an ion, then the oxidation state is going to basically be equal to the charge on the ion. Oxygen is really a good place to kind of start with in terms of oxidation numbers. Oxygen will be -2 pretty much in most cases. The one exception is if you're doing something with peroxide, like hydrogen peroxide, then the oxygen there will actually have a oxidation state of -1, and that's because it's actually peroxide, which will have an oxidation state of -1. How do you know if it is oxygen versus peroxide? Usually the extra 2 kind of lingers. So you'll have like Na, kind of 2O2 type of thing. So those kind of twos kind of linger around, rather than, something like just Na2O, something like that, which would be sodium oxide. So most of the time you can fairly safely assume it's going to be -2, but again, there are a couple of spots where peroxide jumps in there and it is actually -1. Oxidation state of hydrogen is always +1 unless it comes after a metal, and then it's going to be hydride basically -1. So if you have something like LiH, that's going to be +1, and this would be really the negative version of hydrogen, which would be hydride, which would be -1. Everybody in group 1 will be a +1. Everybody in group 2 will be a +2. Thank you. Fluorine will be a -1. Now, when you add up all the oxidation states in a particular species, it does have to equal the overall charge. So if the overall charge of the species is 0, then when you add up all the oxidation numbers, they need to equal 0. If it is -1, then when you add them all together, they do need to equal -1. So if we take a look at bicarbonate here, HCO3 minus, and I would say that if you're assigning oxidation states in a 3-pack situation like this, where you got 3 elements, it's a good idea to go right, go left, and leave the one in the middle for the end, basically. So that's usually a pretty good rule of thumb. So oxygen here is -2. There are 3 of them, which would give us a grand total of -6 in terms of the negative charge. The hydrogen going to the left there is +1. So we do have +1, basically a -6. This overall thing has a -1 charge. So when we add everything together, it doesn't equal -1. So that's a -5. And that would mean that the carbon here, almost like copper, but without a letter, will be +4 in this case. And again, +1 and +4 is +5. -6 is a -1 overall. Now, it's really important as well when you are stating the oxidation numbers or states that you do it correctly. So in this case, hydrogen should be +1, carbon should be +4, and oxygen here is -2. It is not the grand total of everybody together. So when you're stating the oxidation state or number, it's just basically for one by itself, and each one is -2. In addition, for oxidation states and numbers, the charges are also included. So make sure that you do include the charges when you're writing oxidation states. Don't just write the number and let me choose, because I failed chemistry and I will mark it wrong because I won't choose right. Yes. Any questions on that there? All right, so why don't we assign some oxidation numbers for each of these and see what you come up with. So for each of the elements in each of these guys, what is the oxidation state? Bless you. Hmm. All right, let's take a look here. So we'll start with there it is. Start with the lithium oxide here. So again, oxygen is going to be -2 here. And lithium is group 1, so it will be +1. So these guys are our normal sort of what we would associate sort of with our oxidation states. Coming over here to PF3, fluorine is going to be -1, and there's 3 of them, so that's a -3 overall. This thing is neutral, which means it does need to equal 0. So the phosphorus here will be a +3 in this case to get us to 0. So phosphorus is going to be +3, and fluorine going to be -1 in this case. Now, again, like we talked about, sometimes we assume like phosphorus is group 5 and we think it should be -3. And that is the case in an ionic compound. But here we are sharing electrons with the fluorines. And as we know, fluorine is the most electronegative atom in the periodic table there. That means what happens when they're sharing electrons is they're definitely going to share unequally, and those electrons are going to head towards the fluorine. And as those electrons migrate towards the fluorine, that's going to make the phosphorus here more and more positive as the electrons are moving away from it. And again, that's why in sharing electrons here, it actually becomes a +3 oxidation state rather than the normal -3 when it is the recipient of the electrons coming in an ionic compound from a metal. Question up there. This is nitric acid, so we can go right first here, which is -2 there for the oxygen. That gives us -6. Can go left, which is +1 for the hydrogen. And once again, this is neutral, which means in this particular case, I think we're looking at a +5 if my math is not wrong there. So hydrogen will be +1, nitrogen will be +5, oxygen once again is -2, not -6. So -2 is the oxidation state here. Same idea with this. If you remember what it looks like when you drew the Lewis structures in Chem 50. Maybe not, I don't know. Same idea if you look at the periodic table, right? Oxygen is more electronegative, a little further to the right than nitrogen. So same similar situation. Electrons are heading away from the nitrogen, the sharing of electron situation. And again, that's making this more and more positive in this case, where it takes up a +5 charge. Lastly, that's a little dichromate action. That's a -2 there for the oxygen. That's a -14. This thing needed equal -2 overall since that is the charge. There are 2 chromiums, and I believe we need a +12 to get us there. And that would mean that each chromium would actually be +6 in this case, since there's 2 of them. And that means oxidation state here of chromium is going to be +6, and our oxygen would be -2. Yes, ma'am.
So with all the BCM, we focus on the charge. So why did we not focus on the charge?
Say it one more time.
They focus on the charge for that LI2.
So really, what we had on the very first one was an ionic compound. So in an ionic compound, for the most part, the oxidation state and the normal charges that you would associate with those elements will be the same. So in this case, we still did kind of the same thing. Oxygen is going to be -2, and lithium, because it's group 1, everybody in group 1 will always be +1, and just like everybody in group 2 will be +2. And that's basically where a lot of your ionic compounds are going to come from, and they'll basically be the same as the charge in an ionic compound. The other 3 are more covalently sort of bonded in a sense together, and in that sense, that's where we get kind of our different sort of oxidation states that we might normally think of. Yep. Other questions? All right, so this is really important, being able to assign oxidation numbers and states when we get into the heart of the chapter. We're going to talk about galvanic cells and try to figure out, what's being oxidized, what's being reduced. It's a really, important skill, so make sure that you have that. All right, so we talked about balancing redox reactions and half reactions, sort of simple ones last time. And when you have simple redox reactions, basically to balance them, all you have to make sure of is when you look at your half reactions, that you have the same number of electrons in each before you add them back together. And again, if you do not have the same number of electrons in each half reaction, you may require you to multiply a half reaction by a common number before you add them together. The one thing that should always cancel out when we add our half reactions back together is the electrons. And the idea behind that is, again, somebody gets oxidized, going to lose a certain amount of electrons. Somebody else should gain the same amount of electrons. So those electrons should always cancel out. Now, when we get to a little bit more complicated sort of balancing in acidic our basic conditions. There are a few different sort of rules and ways that we balance them. And again, we're going to kind of talk about the steps here to balance a redox reaction in acidic conditions and also basic conditions. And again, just in case you didn't do too much of this in 50, we'll just make sure everybody's kind of rolling on the same page here. If you did, then hopefully it should be a nice review. I hope. Yes, we'll see. All right, I'll do that and a little chromium here. All right. Almost got it all. There you go. All right, so we're going to first balance this in acidic conditions. And I would say that if you are balancing one of these redox reactions in acidic or basic conditions, it's usually a pretty good idea to try to figure out what's going on in terms of who's being oxidized and who is being reduced. So if we take a look at our iron here, our iron on the left-hand side is going from +2 and it's going to +3. So again, in this situation, these are ions, so the charges will be the oxidation states. And as I mentioned before, you can use a little number line if you're not sure. And again, if we look at the iron, it's starting over here at +2 and it's ending at +3. So it's going towards the positive end. And that means in this particular case, our iron is going through oxidation. This would also mean by default, this guy here is going through reduction, but we could do the same thing. We actually just did this guy and we found that the chromium was +6. And on the right-hand side, the chromium is +3. So if we go to the little number line there and we look at chromium, is starting at +6, which would be like over here, and it's ending at +3, which is moving towards the negative direction in this case, which tells us again that it is being reduced. Any questions on identifying that there? Also means throwing out some other words we talked about. Our reducing agent would be the iron in this case, and our oxidizing agent here would actually be the chromium in this case on the left-hand side. As I mentioned last time, remember that all those things, what's being oxidized, what's being reduced, oxidizing agent and reducing agent, they're always found on the reactant side of the arrow, so always on the left-hand side. All right, now that we have an understanding of sort of what's going on in this reaction, this could help us sort of safeguard a little bit later on to make sure we don't screw up too much. So the first thing that we want to do is split this overall reaction into the two half reactions. The way you do that is very simple. You just find the elements that are the same on opposite sides and put them together. So I got an iron on the left and I got an iron on the right. So those two guys make up basically one of my half reactions. I obviously have something with chromium there on the left, and I got something with chromium over there on the right. Now, because we went through it a second ago, we know that this first one is going to be our oxidation half reaction. This one is going to be our reduction half reaction. All right, so now that you have it split off into the half reactions, the next thing you want to do basically is just balance the equation like a normal equation. We want to balance all the elements except for oxygen and hydrogen. So every other element we want to balance like a normal equation, which means we put coefficients in front of things to balance it out. So when we look at the top half reaction there, the iron, we do have one iron on each side. When we look at the second half reaction, we got two chromiums on the left and only one on the right. So just like a normal equation, we're just going to kind of put a coefficient of 2 in front of the chromium on the right. That way we're balanced. The goal is, as we'll talk about here when we're done, is we didn't have this equation balanced basically two ways. It has to be balanced like a normal equation where we have the same number of elements on each side. The other thing that it has to be balanced is the overall charge. So when you add up the overall charge on the left-hand side of the arrow, it does need to equal the overall charge on the right-hand side of the arrow. So it has to sort of be balanced in those both ways when we're done. Now that we have basically balanced everything other than oxygen and hydrogen, usually at this point, we then go after oxygen. And the way that we balance oxygen in this type of situation is we add water, a little H2O, to whichever side needs the oxygen. Now, obviously, if I add H2O to whichever side needs the oxygen, I'm not just adding oxygen when I add the water, I'm also adding hydrogen. So to make sure I'm not unbalanced when it's all said and done, you add water to one side, and then to the other side, you add 2H pluses for every water. And again, that's what's going to kind of keep you from being unbalanced at the end with the hydrogens. By the way, if you ever come across a half reaction where you're starting out with unequal numbers of hydrogen, you can just add H plus to the opposite side to balance it out right at the get-go, and you'll be balanced at that point. So in this particular case, if we look at the iron, there's no oxygen on either side. When we look at the bottom half reaction, we have 7 oxygens there. That means on the right-hand side, we need to add 7 waters. And those 7 waters are going to balance out these 7 oxygens. Now that I added 7 waters, I now put 14 hydrogens on the right-hand side. So to balance that to the other side, I need to add 14 hydrogens because I added basically 7 waters. Any questions on that there? All right, so now that we've balanced all the other elements, we have balanced oxygen and hydrogen. The next thing that we want to do is actually balance out the charge in each of the half reactions. To balance out the charge in each half reaction, we're going to add electrons. So to balance out the charge, we're going to do a little adding of electrons. And since electrons are negatively charged, you need to add it to whichever side needs the negative charge. By the way, when you're doing this, you do not need to get both sides to 0. They just need to be the same number on both sides, whatever that may be. So if we take a look over here, overall on the left-hand side, we have a +2. Overall on the right-hand side, we have a +3. That means in order to get us to balance, I do need 1 electron over here on the right-hand side, because that's going to now give me a -1. +3 and -1 equals +2 on the right to match my +2 I have on the left. Now I'm going to come down here to the bottom one, and you really want to just do it the easy way. I don't know, sometimes people want to go element by element and figure out how many electrons. But if you remember the idea of oxidation numbers, as we just talked about, all the oxidation numbers add up to the overall charge. So it's already done for you, all the individual mass. You shouldn't redo it. So what that means is basically this whole thing is going to give me a +14. This entire thing is going to give me a -2. And that's going to get me a grand total here of a +12 working there on the left. On the right-hand side, this is going to give me 2 times +3, which is +6, and water is 0. So right-hand side, I got a +6. Left-hand side, I got a +12. That means to balance me out here, I need 6 electrons on the left-hand side. And that's going to get me a -6 and +12. That now is going to get me a +6 on the left to match my +6 I got going on the right. Any questions on that there? Now, one of the good reasons, or one of the reasons why we earlier identified which one was our oxidation and reduction half reaction is when we write an oxidation half reaction, the electrons should end up on which side? They should end up on the product side, which they did in this case. And that's a good way to check yourself if you understand that. And when you do the reduction half reaction, electrons should end up on the reactant side. So again, this is a good way to kind of check yourself. You didn't add them to the wrong side or anything like that. By the way, by previously identifying, you should know which side you should put the electrons on, because that should always happen in that direction. Any questions on that there? All right, well, I'm just going to clean up some of my little math here. So get some of this stuff here. All right, do that, and we'll get some of this out of the way here. All right, so we're now ready, after we add the electrons, basically to add both of these reactions back together. But one of the things that we have to make sure of is that we have the same number of electrons in each. In this case, we do not. The top one has only 1 electron. The second one has 6. So we do need to take the very top equation here, basically, and multiply it by 6 so that we have the same number of electrons. I'm just going to write it underneath. So 6Fe2 plus goes to 6Fe3 plus and 6 electrons. Remember, the electrons should always be added to opposite sides like we did here as well. If you ever find yourself adding electrons to the same size, it definitely is wrong. So you definitely mess something up. All right, now that we did that, we're ready to add these together. And remember that anything on opposite sides of the arrow can cancel or reduce down. The one thing that should always completely cancel is the electron. And I think in this particular case, that's everything that we got canceling. Everybody on the left-hand side of the arrow stays on the left-hand side of the arrow. Everybody on the right-hand side stays there. So that's going to get me 14 H pluses plus a Cr2O72 minus plus a 6 iron 2. That's going to go to 2Cr3 plus 7 waters and 6 of the iron 3. And if I did not screw anything up here, we should be balanced, like I said, in both ways. We should have the same number of elements on each side. So if you take a look, you got 14 hydrogens there, 14 there. You got 2 CRs there, 2 CRs there. You got 7 oxygens there and 7 there, 6 irons and 6 irons. So we're balanced in terms of elements. Overall charge, that's a plus 14. That's a minus 2. That's a plus 12. That's a lot of math right now. Or 112 if you write an extra 1 like I did there. Maybe don't do that. That's a plus 12. So that's like I got plus 26 less 2. That's a plus 24 at this point. Over here, we got a plus 6, we got a 0, and a plus 18, which also should equal a plus 24. So we're good on the charge on both sides, and we're good in terms of the elements. And this would be balanced in acidic conditions. Any questions on that part there? Now, what happens if we wanted to balance this thing in basic conditions? Well, if we wanted to balance it in basic conditions, there are a couple different ways you could do it, but probably the easiest way to do it is you do exactly what we just did there. So you basically just balance it in acidic conditions. And at the end, after you balance it in acidic conditions, you can then turn it into basic conditions. So I'm just going to rewrite the equation underneath it here. That's the acidic equation. And now if we wanted to do basic, we're actually going to add, for basic, we're going to add OH minus to both sides. So to balance the equation in basic conditions, we're going to add OH minus not to one side, but we're actually going to add it to both sides. And the question might be, how much OH minus should we add? And the answer is we're going to add an equal amount of OH minus that equals our H plus. So whatever your H plus is how much OH minus you're going to add. So in this case, 14 is my H plus. So I'm going to add 14 OH minuses to the left. And I will also add that to the right-hand side in this case. Now on the side where we have H plus and OH minus, those guys come together to make our friend water. They will make 14 waters. And typically what will happen at this point is you can reduce down the waters as well. So you got 7 waters on this side. That's going to reduce this down to 7 on the other side. You're basically just going to subtract it over to the other side. And that will give me 7 waters plus my dichromate, which is still there, plus my 6 iron 2. We'll go to my 2Cr3 plus and my 6 iron 3 and my 14 OH minuses. And again, if I did not mess anything up here, we now should be balanced kind of the same way, both element and charge. So 14 hydrogens there, 14 there, 7 oxygens there, plus 7 more, give me 14. 2 chromiums, 6 irons, 6 irons. Overall charge here on the left, this is 0, this is -2, this is +12. That's a +10 on the left-hand side. On the right-hand side, this is +6, that is +18, and that is -14. So that's going to give me a net +4 on the right, and a +6 is a +10 overall. So once again, we are balanced both element to element and overall charge. Any questions on that there? Yeah, correct. So you can almost think of like the arrow as like a equal sign. So kind of like subtracting it to the other side. And you would go like normal, whichever side will give you that positive number is usually, you don't usually want a negative thing in this situation. Yeah. Other questions? Now, how do I know, for example, if I look at the very first one I balance in acidic conditions, that I am balanced in acidic conditions? What do I see there that will help me understand that it's acidic conditions? Acidic, I see H plus, like an acid, right? So because I have H plus in there, I know it's balanced in acidic conditions. While this guy down here, which obviously is basic conditions, I know it is basic conditions because I see what in here? I see OH minus, right? So that's how you know when you look at one of these guys, is it balanced in acidic or basic conditions? If it's acidic conditions, you should have H plus at the end. If it's basic conditions, you should have OH minus. Any questions on those steps there? All right. People do this the 50 still? Yeah. Okay. Just want to make sure. All right, then let's just do one here for practice just to make sure. Then make sure. That's the one we just did. Hopefully they got the same answer. Otherwise, it'd be kind of embarrassing, maybe, but not too much. All right. Now, why don't we do this one? Let's do this one in basic conditions. So balance this one out in basic conditions. Also identify what is being oxidized, what is being reduced, what's your oxidizing agent, reducing agent on this one here. I minus plus MnO4 minus. This might be one for next week's lab too. MnO2. We'll do it in basic conditions here. All right, so see what you come up with here. Okay, let's take a look, see how you're doing. So once again, I would probably start out with what's going on in terms of who's being oxidized, who's being reduced. So if we run through our oxidation numbers, this is going to be -1 since it's an ion. Here we will start with -2, and that's -8, and doesn't equal -1. So in this case, the Mn is going to be running a +7 oxidation state. Iodine I2 is how it normally comes, so that's an oxidation state of 0. And coming over here to MnO2, that's a little -2 action there. That's a -4, and that would be a +4 in this situation. So again, if you're not sure, you could kind of roll with a little number line if you want. Iodide there is -1, which would be over here, and it's ending at 0, which means it is moving in the positive direction and it is going through oxidation. By default, that means that this guy is going through reduction, but we could also look at it as well. The Mn is starting at +7, which would be over here, and it's ending at +4, which is moving in the negative direction and would tell us again it's being reduced. That would again mean here that our I minus is our reducing agent. Our permanganate over here is our oxidizing agent in this case. Any questions on any of that identification process there? All right, now that we have it all identified here, we're going to split off into our half reactions. So similar elements to similar elements, so a couple I's, and then things with Mn in it. All right, so like we talked about before, we're going to balance everything other than oxygen and hydrogen. So we do need a 2 there in front of the I to get us 2 I's. On the bottom one there, we have Mn on each side, just one of each. Next, we can move to our oxygens. There's no oxygens in the first half reaction, which, by the way, is our oxidation, and this is our reduction. There is oxygen in the bottom. We got 4 oxygens on the left and 2 on the right. That means that we need a couple of waters here on the right to balance out the oxygens. Once again, since we added 2 waters, that's going to require us to put 4 H pluses on the other side. Now we are ready for electrons. Overall charge here is -2. Overall charge here is 0. So that's going to be a couple of electrons needed on the right-hand side, which will then get me a -2 on the right to match the -2 on the left. On the bottom here, we got a +4. This entire thing's a -1. That's a +3 situation happening. That is a 0, and that is a 0, which means, again, we will actually need 3 electrons over here on the left-hand side. -3 plus 3 gives me a 0 on the left to match my 0 there on the right. Any questions on the electron adding? We also can verify that we just did it correctly, hopefully, because oxidation we added to the right. Reduction there, we added there on the reactant side. So again, we did put it on the correct sides. All right, now that we did all that, we are ready to basically add these together, but I'm just going to erase some of my adding here so we can kind of see what's going on. Again, a reminder that we can't add these together until we have the same number of electrons in both half reactions. And actually, in this case, we do need to multiply both half reactions by numbers. Common number between 3 and 2 is 6. So top guy gets multiplied by 3. Bottom one gets multiplied by 2. I'm just going to recopy that. I'm not sure what's going on over there in biology. We got 6 of those, right? We got 3 I2 plus 6 electrons. Multiplying the 2 on the bottom one there, 6 electrons plus 8 H2 plus 2 MnO4 minus goes to 2 MnO2 and 4 waters, I hope. At this point, we should be able to now add these together. And once again, our electrons should completely cancel. And I believe that again is all that's going to cancel. We're going to end up with 6 I minuses plus 8 H pluses plus 2 MnO4 minuses goes to 3 I2s plus 2 MnO2 plus 4 H2O. And once again, if we were looking for acidic conditions, we should be balanced. Just a quick look at it. We got 6 I's on both sides, 8 hydrogens on both sides, 2 Mn's, 8 oxygens on both sides, 4 and 4 on the right there. Overall charge on the left is -8, +8 is 0. Overall charge on the right is 0. We also know this is acidic conditions because we do see H plus there on the left-hand side, right? At this point, though, we were doing basic, so this is the part where we can turn it into basic. And remember that we're going to add OH minus to both sides, and it is going to be equal to the amount of H plus that we have. So in this case, we're going to add 8 OH minuses to the right and 8 OH minuses to the left. Once again here on the left-hand side, that's going to combine to give us 8 waters. And once again, you typically can reduce it down. So we'll reduce that down to 4 waters left over on the left, plus 6 iodide, plus 2 MnO4 minus goes to 3 I2 plus 2 MnO2 and 8 OH minuses. And now we should be balanced here in basic conditions. And again, we should still be balanced in terms of elements. 8 hydrogens on the left, 8 on the right. 8, let's see there, 8 and 4 is 12 oxygens on the left. 4 and 8 is 12 on the right. 6 iodines on both sides. Overall charge on the left looks like a -8. Overall charge on the right is a -8 as well. So again, balance both ways. Any questions on balancing these things? Which you get to do some of that in lab next week as well. Yes. All right. All right. So sounds like we're on the good page there. So let's get into really the chapter here then. If you want some more practice, there's a few more examples up here. If you want to practice balancing them, you can. All right, so let's get into really sort of the what this chapter really is going to be about, and this is galvanic cells. And galvanic cells are basically redox reactions that are occurring. And in a galvanic cell, a traditional galvanic cell, as you can see here, we could build them out of beakers. And on one side here, in this example, we have zinc, and this is the anode compartment. And in the anode compartment, that is where oxidation basically occurs. So what happens in this particular case is your solid zinc here decides to go for a swim and jump into the pool. And when it does so, it loses electrons and becomes positively charged. Those electrons then travel across the wire, gives you some voltage. Comes down to the other compartment in a galvanic cell, which is the cathode compartment. And in the cathode compartment, that is where reduction takes place. So what happens in this case is the electrons come in, and on this side we have copper, and those electrons join up with the copper ions floating around in the solution, and they get out of the pool. Yes, and they go into the solid phase in that case. Now we have basically the anode to the cathode. Electrons are drawn to the cathode side. You can think of it as being more positive to kind of pull the electrons that way. We also have a really important component to our galvanic cell, which is the salt bridge. And the salt bridge, much like the name implies, bridges both of the compartments there, the anode and the cathode. And it is also made up of a salt solution, an ionic compound, basically, like what we have here, potassium chloride. And what happens here is potassium shoots this way in this example, and chloride shoots this way. You put some cotton in there so it doesn't all fall out at once. It kind of slowly kind of goes and migrates that way and stuff like that. Now, what is the purpose of like the salt bridge here? The purpose of the salt bridge here is to keep everything basically flowing. So if we look at this galvanic cell, we basically have on this side our zinc. And by the way, the zinc is typically in a solution that contains zinc ions. And in this case, they use sulfate. And then this is connected to the other side. And on this side here, we had copper solid. Put it in a beaker so it doesn't fall anywhere. And again, on the copper side, we usually have copper ions that are floating around. And again, I think they use sulfate in this particular case. And again, usually these two compartments are sort of tied together by the salt bridge. Now, if I remove the salt bridge, for example, what's going to happen is this. What's going to happen is we're going to get all these zinc guys jumping into the pool, and they're going to lose their electrons. But the problem with that is as they come into the pool here, I am now going to build up a lot of positively charged zinc ions in there. And I'm going to build up a big old positive side happening now on this side of the beaker. When those electrons come this way, they're going to take this copper out of the solution that's positively charged, and that's going to leave my negative ion in the solution. And this side is going to eventually build up a big old negative side. And we're going to get a buildup of positive charge on the left-hand side, a buildup of negative charge on the right-hand side. And again, this is a situation if you took the salt bridge out. Why would that be bad in a situation where I want my electrons to go to the cathode side? This is my cathode, this is my anode. And I took my salt bridge out because I said I did not want to do that step. And I build up a bunch of negative charge on that side and a bunch of positive charge on that side. Is that good for my electrons to flow? It is not, right? Because opposites attract and things with the same charge repel each other. So you got two bad things that just happened. You got these negatively charged electrons that are going, why am I leaving? This is like nice and positive over here, right? Secondly, why would I come over to this side? That's negatively charged. I definitely don't want to be over there. So the purpose of the salt bridge is to prevent this from happening. If this did happen, your flow of electrons is essentially going to stop and your cell is not going to really do much for you or create any type of voltage. And that's why when you look at the salt bridge in this particular picture, the negative ion is heading over here to this side. And again, that's going to prevent that buildup of positive charge by throwing some more negative in there. And the positive ion on the salt bridge is going to head this way. And again, to kind of prevent the buildup of the negative charge over there. So the purpose of the salt bridge is to keep everything sort of functioning and moving correctly and to prevent any buildup of the wrong charge that you need, that you really don't want, to allow those electrons to happen and travel to the other side. Because ultimately, what we kind of want is a little bit more positive there on the cathode side to kind of encourage those electrons to kind of come to the other side. And again, the purpose of the salt bridge is to not end up in this situation where the electrons are not going to want to kind of travel one way or the other. Any questions on the purpose there of the salt bridge? All right, so as we can see here, if we look in this particular example, our zinc is going from 0 to +2, again, becoming more positive and going through oxidation. And again, we'll jump into the solution. As you can see here, it goes from the solid electrode off into the solution, floating around as ions. On the other side here, we have our copper, which is picking up those electrons that the zinc is giving away. Is going from +2 to 0, becoming more negative in this case, and going through reduction in this case. And then what we see here is the copper will come out of the pool again and kind of become solid copper at that point. What is the purpose of the electrons? The electrons go out through the wire and do some type of work, right? If it's basically similar to batteries. I mean, but batteries in your device, there's little wires there, right? So it does a redox reaction, sends those electrons off, and your calculator turns on. Unless you drop it. I don't know, maybe turn on so much there. We can also obviously add these two half reactions together, and we do get our overall reaction, which is showing again our zinc going from 0 to +2, and our copper going from +2 to 0 in this case. In this case, we would add both of those half reactions back together. Electrons would cancel out, and we'll be left with the overall reaction. Any questions on the components of a traditional galvanic cell here? All right, so when we talk about the galvanic cell, there is a difference in electrical potential between the anode and the cathode, and that's sort of what drives the reaction or electrons from one side to the next. Here is an example of that, and if you zoom way in there, you can kind of see the salt bridge that kind of connects those two containers right there. We used to build them like that. We don't. We now use like little spot plates to build them, but we don't build these big ones anymore. A few things that we talked about here, which is cell voltage. A volt is 1 joule of work per coulomb of energy transferred. So a volt basically is a joule over a coulomb, which is a unit of electrical charge. Sometimes this difference is referred to as the electromotive force or the EMF, or the cell potential. So in a problem, if you're asked any of those three things, calculate the cell voltage, calculate the EMF, or calculate the cell potential, they're basically asking you to calculate the cell voltage, basically, in that problem. Like I said before, that sort of difference between the anode and the cathode is what kind of drives those electrons to the other side. Now, there is a way that we sometimes represent galvanic cells in sort of a shorthand, and this is what is referred to as a cell diagram down here. And we basically have a single line between our two components here of our anode compartment. We have a double line here, which is representative of the salt bridge that separates the two components. We also, again, have a single line between, again, our cathode component. A cell diagram always goes anode to cathode is usually how it's always written. So anode to cathode is how it's written. You also see some other things that sometimes find their way into these. The concentration of the ions, which are 1 molar. By the way, 1 molar is standard concentration. So these would be standard conditions. We also sometimes have electrodes that are an anode or a cathode that's actually a gas. So in a situation where we don't have like a physical electrode that we could use, we will sometimes use some type of inert solid like graphite, platinum, something like that as like the physical electrode that we stick in there. And because it is technically a gas, we will also sometimes see pressures indicated inside the cell diagram. And again, atmospheres, 1 atmosphere is standard pressure and stuff like that. How does this work in terms if you wanted to go from the cell diagram back to your equation? Well, it's pretty straightforward. This is usually the reactant, the product, the reactant, the product. So zinc reactant, zinc product, copper 2 reactant, solid copper product. So that's how you could kind of go from the cell diagram backwards. It goes reactant product, reactant product. Again, if you do get a cell diagram that's got some extra stuff in there, like maybe platinum or something like that, you typically don't include those in the reaction, but they are, again, sometimes included in the cell diagram. Any questions on that? So let's talk about our reactions here and what is sometimes referred to as the standard reduction potential. The standard reduction potential is also sometimes abbreviated as an SRP. There's actually a table of SRP values that you'll need in this chapter that you could look up. In this particular case, we got our zinc on our anode side and our hydrogen in this case on our cathode side. And as you can see, hydrogen is actually a gas. So once again, here we do use platinum as like the physical electrode in this case. And you can see it is included in the cell diagram to indicate that. Also, because it is a gas, you can see that the pressure is also included in the cell diagram, as opposed to our zinc over here, where it is obviously a solution. It has a molarity. Here, the zinc is going from 0 to +2, which again is becoming more positive, going through oxidation. The hydrogen here is going from +1 to 0. It is getting reduced in this case, becoming more negative as you draw on that number line, +1 back down to the left there to 0. Once again, adding these together, our electrons cancel, leaves us our overall reaction there on the bottom. And as I mentioned before, if you look at the cell diagram, reactant, product, reactant, product in this case. And again, you can see zinc reactant, zinc with a +2 charge product, H plus reactant, and H2 product. Again, you might have to do a little bit of balancing as well, but that's again how you could kind of orient it into the equation if you're just given the cell diagram. And once again, always anode to cathode in this case. Now, the standard reduction potential is used to help us decide, the sort of E values or the standard reduction potential for every sort of element. Now, in chemistry, usually when they want to kind of measure something and they maybe don't have a direct standard to use, they sometimes will just assign somebody as a standard to use for their calculations. And in the case of the SRP values, they use the hydrogen electrode, or what is sometimes referred to as the standard hydrogen electrode, abbreviated as the SHE. And that is used basically as the standard to compare everybody else to. They arbitrarily sort of assigned it a value of 0 volts. So they gave this guy a value of 0 volts, and they basically just kind of hook up galvanic cells, other things with the hydrogen, measured the voltage, and they could figure out the standard reduction potential for everybody else. Why are they called standard reduction potentials? Because when you go to that table, they look just like this. Every single reaction is written as a reduction reaction. So everybody will have their electrons on the left-hand side of the arrow, as we see in a reduction half reaction, and they're all written in that case. And again, here, our hydrogen has a value of 0. So if we take the standard hydrogen electrode and we hook it up with something like zinc in this case, and we measure the voltage, we end up with a voltage of 0.76 volts. And we can use that and this equation here, which will help us determine the cell voltage here in a galvanic cell. And this is E of the cell is equal to E of the cathode minus E of the anode. And in this particular case, our zinc is our anode and our hydrogen is our cathode. And again, our voltage in this cell was 0.76 volts from the voltage meter we hooked up. Our cathode, which was our hydrogen, is 0 volts minus our anode here, which was our zinc in this case. Bringing the zinc to the other side and subtracting the 0.76 volts over. That gives us the SRP value there for zinc. A very simple way of doing it by basically hooking up the cell. Now, this formula is an important formula. It will allow you to calculate the cell voltage in a galvanic cell. You would go to an SRP table, which we'll take a look at in just a second, and look up the values here. Now, what I'm going to say to you may not make sense at this point, but it will hopefully make sense shortly. But there you will sometimes see this equation written two ways. And one way is what we see there, which is E of the cell is E of the cathode minus E of the anode. You may also see people use this cell like so. E of this cell is equal to E of the cathode plus E of the anode. And they are very similar, except that one obviously is a plus sign and one is a minus sign here. So the rule is this: when we go to this table of SRP values, they're all reduction reactions. The problem, though, is in a galvanic cell, both sides are not reduction reactions. One side is an oxidation reaction on the anode side, and one side is the reduction reaction on the cathode side, which means when you go to that table, the value that you see is actually the wrong value for the anode. It actually should be reversed. And when you reverse one of these reactions, the sign changes. So, for example, if I have this guy here, which is my zinc plus my two electrons, go to my solid zinc here, and I go to my SRP value table here, and I find obviously my 0.76 negative volts. And that would be if I needed zinc to be my cathode, because that's how it's written. It's written as a reduction. But if I needed my zinc to actually be the anode, I would actually have to reverse that reaction, because in the anode situation, the zinc is going to lose those two electrons. And this would be like my anode reaction or my oxidation reaction where they're given off. And basically what I did there is reverse the reaction. And what happens is the sign of that guy will now become positive 0.76 volts. So if this is my cathode reduction and I needed an anode guy, that's zinc, which is my oxidation, I would reverse the reaction and the sign of the value I find in the table changes. Now, back to the equations that I put on the top before, what is the difference between them? Well, in some cases, all you're really interested in is like, what is the cell voltage, right? And you just want to go to the table, find the two things, find the values. So if you go to the SRP table and you do not want to have to change the sign of the anode compartment one, you should use the subtraction, because that's what the subtraction is there for. It will change the sign for you. Now, if you want to do everything like perfectly correct, which is like, hey, I need to reverse that reaction and change the sign that you find in the table, then you already changed the sign and you should add them. So that is the difference between those two. If you change the sign on the anode that you find in that table, you should add both of them together. If you want to just leave everybody alone in terms of their sign, you should subtract. I would recommend choosing a way and sticking with it so you don't end up changing the sign and then subtracting and changing it back or anything like that. So you'll see it both ways. I personally use the -1 because I just want to go to the table, find the value, and just pop them in there as soon as I identify cathode and anode. But if you want to change the sign of the anode, then definitely make sure you add it. And again, we'll do some examples where obviously it'll be a little bit more clear, but that's sort of the idea behind that. Any questions on that? All right, so here is a table of SRP values. Maybe. Just love this table. It doesn't want to go any further. Maybe. Come on. No. This table is like a locked-in table. It just does not want to go any further. Just skip that entire table view there. All right, here's another table. In case you like that. And here's a third table. And you have a different table, I think, in your book as well. I think maybe that first one was your table. But taking a look at these tables, a couple things here. We can see, we'll take a look at this one here. Once again, when you go to this table, everything is written as a reduction reaction. All the electrons are on the left-hand side, obviously, of the arrows here. And again, that's what I was saying a second ago. If you needed to do the anode compartment, technically speaking, you would have to reverse the sign that you find in there and reverse the equation. So again, if you're going to do that, you want to reverse the sign, add them together. You want to keep the sign like you find it, subtract them. Now let's talk about a couple of things about these, and some of these we just touched upon. First off, when you see an actual half reaction, the E value that you see should be for how it's written. So technically, as I just did that zinc one a second ago, if I was to write that zinc reaction technically as the anode, really the value should be positive 0.76 volts. If I was going to write it as the reduction or cathode, it should be the negative 0.676 volts. So really the E value should go with how it's written, which is why people are like, no, you should add them and change the sign yourself, because technically you should do that. Now, how do I know if I'm going to build a great galvanic cell out of these two things, what's going to be my anode and what's going to be my cathode, right? So if you are not given any information about what is happening, you're not given an overall reaction, you're not told in words what's going on, the more positive E value that you find on the SRP table, that has a greater tendency to be reduced. And in a galvanic cell, the anode or the cathode gets reduced. The cathode gets reduced. So if you're building this galvanic cell and you're not given any information other than, hey, you're going to put zinc and copper together and build a great cell, you're going to go to the table, and whichever one's more positive should be your cathode. So the more positive SRP should be your cathode. And the reason for that is it will really give you a spontaneous reaction that's going to occur when you do that. Now, with that being said, if you are actually given a reaction, you should actually look at the reaction and figure out who's being oxidized and who is being reduced. It may not agree with the table. So, and the reason they gave you that reaction is because that's the reaction they want to look at. So if you are given a reaction, you have to actually look at it and decide who's being oxidized and who's being reduced. If you're not given an overall reaction, then you can just simply go, the more positive one should be your cathode. The less positive one should be your anode. The half reactions are reversible, as I mentioned, so you can flip them around. When you do flip one of these reactions around, the sign that you see in the table for the E value will change. So if it's negative, it will become positive. If it's positive, it will become negative. The other thing that is not affected when we do this is sometimes we obviously need to add our half reactions together to get the overall reaction. And as we've seen, sometimes we do need to multiply those half reactions by a number. You can multiply the half reactions by a number, but you do not change the E value. So it doesn't matter if you need to multiply a half reaction by 2. You know, we had zinc or something, and it was negative 0.76 volts, but like I need to multiply this by 2 to balance out the electrons. This does not get multiplied by 2, so it stays the same. So it doesn't matter what you're multiplying by to balance out the equation. It will not have an effect on the E value. Any questions on that there? All right, so let's try one here. Here are a couple of SRP values. We want to know, what is the cell voltage for this galvanic cell? Why don't you also balance the equation as well? Identify the anode and cathode. Okay, so since we're today on here, let me go over it here just to illustrate what we were just talking about, since we just kind of talked about the adding or the subtracting. So let's first take a look at these are obviously values that you could find in the table, and you will have to probably refer to the table that's in your book for homework problems and stuff like that. The table obviously would be provided for you, obviously on quizzes and exams. And then in this case, we're building a galvanic cell out of basically cadmium and chromium here. We're under standard conditions, 1 molar for each of them, right? So they really don't tell us who is who in this situation. So we can use the SRP values to help us decide who should be the cathode and who should be the anode. So we're looking for whichever one in this case is the more positive one, and they're both negative. So out of the two, this guy is actually going to be just a little bit more positive than our other one. So that would be that this guy's going to be our cathode, and by default, this guy would be our anode in this case. And once again, we weren't given any overall reaction, so we could just simply use the SRP values to determine that. I'm going to actually balance the equation here first. That means, technically speaking, this equation is good. It's written correctly. It's written as a reduction reaction. This equation is not so good because it should be a oxidation reaction, which means that technically speaking, the anode is the one I should have to reverse in this case. And technically speaking, if I reverse this reaction, what's going to happen to my E value is it's going to go from negative 0.74 to technically positive 0.74. This is what is sometimes referred to as an SOP, a standard oxidizing potential, because this is an oxidation reaction in this case. Now I have both of my equations written correctly to get the overall reaction, but I do have a situation which is when I look at this reaction here and this reaction here, they do not have the same number of electrons. And that means that I really have to multiply this guy by 3 and this guy by 2. And if I rewrite those underneath, I will end up with 3CD2 plus 6 electrons go to 3 cadmiums. Once again, even though I multiplied by 3, it has no effect on the SRP value. I'm going to multiply the bottom guy by 2, which will give me 2 chromiums. Goes to 2 chromiums with a +3 charge and 6 electrons. Once again, even though I multiplied, will have no effect on that value. This will still be positive 7.4. Now, when I add these together, my electrons will cancel, and I will end up with 3 cadmiums with a +2 charge, plus 2 chromiums, go to 3 cadmiums with no charge, and 2 chromiums with a +3 charge. It is actually balanced. I have 3 cadmiums on both sides. I have 2 chromiums on both sides. Overall charge on the left is +6. Overall charge on the right is +6. So it is completely balanced. First off, any questions on the writing of the equation? All right, let's get to the actual question, which is I want to calculate E of my cell, right? Now, if I want E of my cell, I could take the cathode minus the anode. And if I'm looking for just the cell voltage, I'm going to go to my table. I'm going to identify which one's which. And if I'm going to use the subtraction, I am not going to change the sign of the anode. So this would be negative 0.4 volts minus a minus 0.74 volts. Again, the negative here is to change the sign for me, basically, when I subtract it. And that's going to give me a cell voltage of 0.34 volts. So if I was just looking to calculate the E of the cell, I'm not going to change the value here if I'm subtracting. Now, if you wanted to change the sign like we did down here, because I did change the sign, I could calculate my E of the cell by adding those two together, E of the cathode plus E of the anode. And that would be basically these two numbers, minus 0.4 volts plus a 0.74 volts, give me 0.34 volts. So that is what I was talking about by either change the sign or don't change the sign. So if you do not want to change the sign and it was just like, what is the cell voltage? You could go to the table, pop it in there with this minuses. It will change the sign for you. If you want to change the sign like we did here on the bottom, then you need to make sure you add them. Again, don't do both. Yeah. Any questions on that there? All right, we'll wrap that up for today.